Alright, I'm going to start this video out with, as I usually do, a brief introduction to the product, the subject of this video, using Chuck Penson's excellent book, Heathkit Test Equipment Products. So far I haven't delved into any of the Heathkit frequency counters. This may be the first one, or it may be an outlier. It may be the only one I do. I was always intrigued by this particular model, which is why I snarfed one up on eBay when it became possible to get a clean one in fully operating condition. And this is the IM-2400, a 512 megahertz frequency counter. It was offered for 10 years starting in 1980. Introduced for Christmas in 1980. It features a 7-digit LED display and covers frequency ranges from 50 Hz to 512 megahertz. It has two separate inputs, one ranging from 50 Hz to 50 megahertz with an impedance of 1 megaohm, and a 40 megahertz to 512 megahertz range input with an impedance of 50 ohms. So very different types of signal. Indeed, they recommend that while you can use just a simple BNC connector pair of test leads on the higher impedance input, you're really recommended to use a 10 mega ohm times 10 oscilloscope probe on that. That's the best all-around type of cable for that particular input. And then on the higher frequency one, you really need to use something that's designed for 50 ohms, and that can be quite a range of things, of which the manual suggests several options, including just using a simple whip antenna on it, or a simple coil connected up to a BNC connector, and the coil held next to the coil of something in a radio circuit, for example. The low side input, meaning the lower frequency range input, can go up to 150 volts RMS, and that's up to 100 kilohertz. Once you start going above 100 kilohertz, and remember that input can go to 50 megahertz. Once you get above 50 kilohertz, they recommend not going any more than 10 volts. And then the high side input, which is the higher frequency one, it's just set up to use a maximum input voltage of 5 volts RMS. It has a selectable gate time of 0.1 seconds or 1 seconds. It has a resolution of 1 hertz on the 50 megahertz range, assuming you're using a gate time of 0.1 seconds, or a resolution of 100 hertz above 40 megahertz with a gate set at 1 second. One of the very last test equipment products that Heath had in their catalogs at the very bitter end of their operation as a kit manufacturer. It is nominally powered by a set of rechargeable NiCad cells, 5 of them comprising a 6-volt not a rechargeable battery, or you can use it with a recommended Heathkit power supply or something equivalent that provides something a little bit more than 6 volts. The recommended supply puts out about a little bit more than 7 volts DC. So I've already covered the basic appearance of the thing. It's sort of like a large handheld calculator, and it has the 2 BNC connectors for the 2 different frequency ranges and an on-off switch. Then the front of it is the range switch, higher, low range, and the time base, 0.1 seconds or 1 second. So with that, let's look at the actual artifact. Alright, here's the main circuit board, and then behind a shield and support frame is the actual frequency counter. So this is all front end and power supply circuitry here. Input conditioning and scaling, and then all the heavy lifting is done on this board. So basically a frequency counter in a single large-scale integration monolithic IC. And just as with some of their other products from that same time frame, this is an Intersil product. They of course are famous for their series of single chip multimeter, or at least voltmeter ICs that would work with either LCD or LED displays depending on the version of the chip. Practically do everything for you except input scaling. And just like that, this is a frequency counter in a chip. It's designed to go up to 10 megahertz. And this is part of a series. There's actually 3 or 4 chips in this series that work with different types of displays. I think they're all LEDs, but you can get ones for common cathode, common anode. You can get a more general purpose one that has a lower range but can also be used to do other frequency counter types functions like totalizing or determining the period of a signal. This model here is the D version, and all it can do is frequency counter. It's designed to drive an 8-digit LED display. This meter only uses 7 digits. It has its own crystal and a trim capacitor there to fine-tune the crystal for calibration. And there's really nothing else on here, just the immediate support chips, then the master chip and the LEDs. It looks like the chip also handles all current limiting or current control for the LEDs, so you don't have to have a bunch of resistors in the circuit for the LEDs. Now down here at the bottom of the main board we have the power supply. There's the input jack. There's a filter capacitor, a Zener diode, a resistor, a power pass transistor. Those are all there to generate the needed internal regulated 5 volts that everything runs on. There are the cut-off leads for the NiCad battery. The previous owner of this had obviously decided to dispense with the NiCads probably before they would leak all over everything and just run it off the AC power supply. I could reinstate the NiCad battery, but I have no intention of doing so. Otherwise, we have 74196 in there and some surrounding components. We have the 2 slide switches for selecting frequency range and time base, and 1, 2, 3, 4 other support ICs. And as we get closer to the front end up here, the layout is pretty logical. Oh, by the way, the power switch is up there, and it isn't even connected to the circuit board right there. It just has a pair of leads running all the way across the board down to right where they're needed, next to the power jack. So we have this input here coupled directly through a capacitor and then to the circuit board, whereas this one is connected directly to the circuit board. Each jack has its own separate ground connection to the circuit board, even though they're both on a metal plate, common metal plate. That's good practice. There's also a little bit of a shield here. Pretty much everything you see up in this area is preamplification, limiting of the voltages, and amplification where necessary, and pre-scaling. Because again, this meter entirely goes up to 512 megahertz, and there's only a 10 megahertz maximum input to this frequency counter chip. So obviously there has to be some pre-scaling, dividing down of the frequencies. So this is the 512 megahertz maximum 50 ohm impedance input, and that's its front end circuitry there, and its amplifiers, as I pointed out before. And then here's the lower frequency but higher voltage and higher impedance input, and that's why it has a very different set of front end components. And that's how the frequency counter subboard mounts. Okay, here's the case front. Just a very simple case, couple of pads to hold the batteries in if you had them, and the red Lexan filter. And it fits in like that. The back of the meter has a fold-down kickstand. Holds at a nice viewing angle. Here's the Heathkit power supply. Its model number doesn't match directly the power supply model number shown in the catalog, but that's a weirdism of Heathkit. So the physical part is just got electromech, that's the manufacturer. It just has their own information on it, to the exclusion of any Heathkit information. And then on the back they just have embossed on there their part number, which is 15093, but in reality it also has a model number, which is quite different, and I think that's an item of confusion. Anyway, this is a 7.3 volt DC output up to 350 milliamps. And so I've got the power supply plugged in. I have a Siglent function generator here, which I'm going to crank down. I've got it set up for a 4 volt peak to peak right now, and I'm going to crank that down to the lowest frequency that this machine is capable of reading, 50 hertz. So I'm going to turn the unit on. This is still turned off, and there I get a nice display. It's basically sitting at 0. I have it selected to the 50 hertz to 50 megahertz range, and I have the time base set to 1 second. And I'm going to turn the output on, and I get a reading of 5, actually 0.00005 for 50 hertz. And that's the first clue that something is unusual. There is no indication on this display saying that this reading is in megahertz. You might assume it would be in kilohertz or something. It certainly isn't in hertz. Not with a range this high. You'd never get meaningful numbers with only 7 digits. So in fact, this meter, this frequency counter, is always in megahertz display mode. Any number it presents, regardless of any switch setting or input, is always in megahertz. So 0.00005 megahertz is 50 hertz. So now I'm going to crank my function generator up to 100 hertz, and I get this. I'm going to go to 130. Now what happens if I go to 0.1 seconds? I lose resolution, but it responds faster. Go back to the slower response, but I get the higher resolution, showing me that extra digit. So I'm going to crank her up here to 530 hertz. Let's go for the glory now. Let's Crank it up to 1.43 kilohertz. .43 kilohertz. .371 kilohertz. 0.43. It's right on the money. It's showing exactly what this is putting out. So I'm at 3.871 megahertz, and now we've got over the decimal point here, 3.871 and change megahertz. $24,871. And this signal generator does not put out higher than 25 megahertz, which is basically what it's doing now. And obviously with this extra resolution, it shows that it's just ever so slightly different. I'm not sure which is more reliable at this point. I suspect that at such a low resolution, the Heathkit's probably the less reliable of the two, but who knows? This might actually be the one telling the truth. Anyway, so that's just a very quick approach here. I don't have anything that'll easily generate much higher frequencies, but I will try putting the whip antenna on and just seeing what I can get on the other input range. I'm going to turn this off, and it should drop back to 0. Yes, it does. Okay, I have the whip antenna here, but it's on the other input, and it's not reading that input, so I need to switch over to that, and it is picking something up. I have no idea what. Something in the 10 megahertz range, some local radio station, something generated by the microprocessors in one of these products. Could be any number of things. But it is picking something up. A bit of an overview of the manual. Even though this is a piece of test equipment, and most of Heathkit's test equipment had the full-size 8.5 by 11 manuals, they, for some of these handheld ones, they did go with the small manuals, usually associated with the less expensive products. So, introduction. The IM-2400 is a handheld frequency counter. It's a compact, easy-to-use instrument. Accurately display measure, can accurately measure frequencies to over 512 megahertz. Designed for portable use. Excellent accuracy is assured by a modern digital design and a 10 megahertz crystal oscillator. And here it mentions the PS-2401 for 120 volts AC operation, and the PS-2405 for a 240 volt. And to the best of my knowledge, you know, any number of power supplies would actually work. Again, as long as they have the 0.1 inch tip ring or tip sleeve type of phone plug for the power. I actually have a video making a clone of the PS-2350, which is another power supply used by some of the other instruments, including their handheld digital multimeter, and that one would also work with this. That's a 6-volt design, which would work just fine with this frequency counter. So, as usual, we've got a parts list. Everything's described in great detail. All the transistors, integrated circuits, miscellaneous parts, assembly of the battery pack, circuit board assembly. I won't go through all the nitty-gritty here, but quite a few pages of detailed assembly. Then they even have you make the insulating paper piece for the shield and support plate that goes behind the frequency counter subboard. Calibration. There are two calibration procedures. If the builder has access to a 50 megahertz frequency counter and a signal generator capable of delivering up to 50 megahertz, then that can be used, or it can be used as a laboratory standard. If those instruments are not available, then the calibration without instruments procedure is used. In that case, it's tuned to an AM radio station. You tune your AM broadcast radio to a station of medium volume and temporarily connect an additional antenna to the antenna connector of the radio. You lay the antenna over the oscillator section of the counter. So again, it gets kind of funky there, but apparently it works. And then you can also use the calibration if you have laboratory instruments. Final assembly. And here are some things it talks about. If you're using the low frequency input with a 1 megohm impedance, when you measure high amplitude and fast rise time pulses or square waves with a high sharp rise time, then it's recommended you connect a small resistor, perhaps quarter watt, in something in the order of 10 kilohertz in series with a simple test cable, and use the other end of the resistor as the probe. That is due to reflections that you'd get with the high rise times or the fast rise times, which could cause erroneous readings or possibly even damage to the equipment under test, not necessarily the frequency counter. But they say really the best thing to do is get a 1 megahertz divide by 10 oscilloscope probe. That decreases the input sensitivity somewhat, but it does provide better isolation, and it solves a lot of the potential issues. When you measure frequencies from a transmitter, blah, 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 and then if you're in the higher frequency range, you have to properly terminate with a 50 ohm, you have to properly terminate a 50 ohm transmission line. If you use test cables other than 50 ohms, it's necessary to use a matching pad to eliminate reflections and capacitive loading. And then they talk about how you can use the optional telescopic antenna. You can also make a simple coil connected to a BNC test cable and use that for certain types of test. And it talks about the maximum input voltage and how it's related to the frequency you're measuring. There's a little chart for that. Talks about the display and how there's the two ranges and the two time bases and how that affects resolution. Talks about battery charging. There's an in case of difficulty in troubleshooting section. Not a very extensive one, actually. It's all very general, and then they have a tiny chart. Simple page of minimal specifications. Flowing over to the other side. A general theory of operation just on one page, talking about the essence of how it works. And then it has a nitty-gritty, more detailed circuit description of each section. It talks about how there's actually different digital signal levels you might want to read, and how that influences the input. And it also talks about within the meter itself, it's using TTL logic, CMOS logic, and ECL logic. And the ECL is used especially on the higher frequency stuff. It talks briefly about the 50 megahertz input amplifier and about the same amount of text about the 512 megahertz amplifier. Talks about the input selection and how that's accomplished. Talks about the actual frequency counter board, and it pretty much just says, well, there's one chip that does everything, and it doesn't really go into any more detail than that. It talks about how the decimal point is selected in one long or two long sentences. A very brief rundown on the power supply. Somebody wasn't putting a lot of effort into the circuit description on here. You've got your circuit board X-ray views for the two boards. And then the semiconductor identification charts. Diodes, transistors, the various ICs. And then finally the big IC for the frequency counter function itself. And that's the end of the manual. Okay, the schematic diagram. What I usually finish these test equipment videos with is a fairly detailed run through of the schematics. So I'm going to do that here. I'll start out with the power supply. Alright, the NiCad battery, assuming it's fully charged, is somewhere in the area of 6 volts. And there's the power switch up here, and the AC power supply input jack. Normally, if nothing's plugged in here, then the plus side of the battery just goes through this 42 ohm resistor, or 47 ohm resistor, through the power switch and into the regulator. If you do plug something in, then the battery is disconnected, although it still can go through the resistor. I should point out that when there is nothing plugged in here, the jack shorts out the resistor, so the battery does not actually have to go through the resistor. The current coming from the battery goes through the jack, bypassing the resistor, and then directly in here, and you get about 6 volts into the regulator input. If you do plug in the power supply, then let's say it's probably about 7 volts or so, as already discussed, it disconnects the battery from direct connection and then produces the, or applies the 7 point whatever volts through the power switch and to the input of the regulator section. But then this resistor here becomes a charging resistor, and that higher voltage than the battery voltage allows charging current to go backwards here and charge the battery, whether or not the frequency counter is turned on or not. Then for the actual voltage regulator, it's just a Zener diode with a small filter cap across it, and then the reference voltage provided by that is applied to a very simple NPN series pass power transistor, and that just produces a regulated 5 volts here for use by all of the circuitry. Okay, looking at the lower frequency input circuit, again, this is not anything to do with the counter itself. This is all just signal conditioning. So we come in, we have a 1 mega ohm resistor with a capacitor coupling and a small ferrite bead, and the common of the input connector is just tied to circuit ground. And then we have another resistor here going to a couple of clamping diodes pointing in opposite directions, so they as the frequencies get higher, then this resistor is diminished because this resistor, or this capacitor, starts letting more go through it, and that effectively makes this like a smaller resistor. And by doing this, we are able to clamp the input voltage, which can be, again, up to 150 volts RMS peak to peak. or 150 volts RMS, I should say. But at higher frequencies, it really needs to be a lower value or lower voltage, but it's quite capable of working just fine at lower voltages like logic level signals, or the 4-volt peak-to-peak signal I was doing it in the demonstration a little while ago. We have here a 2-transistor front end. There's an FET followed by a bipolar transistor, and the collector is 10 ohms up to the positive supply. The emitter is 220 ohms to circuit common. Then both the collector and the emitter are capacitively coupled into this 1, 2, 3 chain. This is a high frequency amplifier, really intended for RF signal amplification, and it's done in 3 stages. It's all in one IC. And there's a couple other things. This IC also includes a reference voltage, which is used internally, so it's sort of an all-in-one RF amplifier. The signal here and signal here each have a resistor to ground. It makes it look like this is the power supply, but it isn't. It's just a 220 ohm resistor from this point to ground, and another 220 from this point to ground. And then the same thing, because these are differential amplifiers, there's complementary signals, I guess I should say, here and here. And so the opposite side's also tied through a 220 ohm resistor to circuit common or circuit ground. But once we get past this point, we're not using the differential after the first 2 stages, so it has the output just directly tied to ground here. It doesn't go anywhere. And then the 3rd stage has some biasing on it, and basically what this is doing along with this bipolar transistor is it's converting the voltage levels. This chip, in order to be high frequency at the time this was done, it was an ECL circuit. Its signals are compatible with ECL, and that's a different set of signals than the other logic in here want to use. So this acts like sort of a level shifter. It's actually labeled as an ECL to TTL translator, and that's referring to the voltage levels, so it satisfies a TTL logic circuit, what it expects for a logic high and what it expects for a logic low. So again, a couple of diodes and a transistor and a couple of resistors accomplish that. Then, because this is not a very low impedance output, it's using a simple emitter follower transistor to get more drive out of that, essentially. So all we've really done is we've clamped the heck out of the input. It can't go above, once it gets past this, it can't go above a diode's forward bias or a forward voltage from ground. And then it gets amplified. So knock a big voltage down and then amplify it back up by a known amount, and you end up with everything coming out in approximately the same voltage, regardless of what you're applying out here. A small signal would be made bigger, a big signal gets made smaller. And basically what you have coming out of here is a 50 hertz to 50 megahertz signal in the low frequency range. Now for the higher frequency input, which is designed for the range 40 megahertz to 512 megahertz, or even a bit higher, and recommended no more than a 5 volt RMS maximum input. This is intended for a 50 ohm impedance, and the first thing we do is we have a signal clamper, and it actually has a diode bridge here. It's made out of 4 discrete diodes. But look at the way they're pointing. Let's say that after the capacitive coupling here, the signal tries to go positive. Well, it's blocked by this diode. But it can get through this one, only to be stymied by this one. If the signal tries to go negative, it'll conduct this way, but then it's blocked by this one. So how does the signal get through here? It's not being used as a rectifier. It's being used as a clamp. And there's the positive power supply up here and ground down here. 1800 ohms, 1800 ohms. So it's being held between ground and the 5-volt power supply. And actually what this ends up doing, these are hot carrier, also known as Schottky barrier diodes, and their particular characteristics are such that it ends up clamping the signal to about 300 millivolts. But the signal itself can't get through by normal action of the diodes. And I was a little stymied by this at first. I looked at it, I couldn't quite understand it. I knew I was forgetting something. But luckily the brief Heathkit write-up is as without detail as it is, a little bit vague. It did mention that under these conditions, these diodes have capacitance to them, and it's actually in this frequency range, it's the capacitive coupling, or not capacitive coupling, but it's the capacitance of these diodes that's actually responsible for passing the input signal through, not the normal diode action. So the diode action is used for clamping. The capacitive internal capacitance of these diodes is responsible for coupling the signal through. And it's applied to the input of this RF amplifier. It's a single chip RF amplifier. So once again, the signal's been knocked way down by the clamping action here, and then this builds it back up. It's also a differential amplifier, but we're only using the positive side of it, if you will. Pin 10 is the positive input, and pin 3 is the corresponding output. But to keep this balanced, and needs to be balanced to operate properly, they have to reference through, with AC coupling, they need to reference it to circuit ground. So that's why there's capacitors from the negative input to ground, and a capacitor through a couple of resistors on the output to ground. That's all about just balancing this amplifier. But basically your signal path is through here. And then it's conditioned again by a couple more resistors and a capacitor, and it's fed into this. This, because of the frequency range, is another ECL logic circuit. It's got to be handling, 512 megahertz at least. It's basically just a divider. This chip can be a 1 or divide by 10 or a divide by 11, depending how you set up the programming inputs. And the way Heathkit's using it here, they're basically using it as a divide by 10, but they're doing something cute by tying one of the programming inputs back to an output. And I admit I don't exactly understand what's going on there. And they don't explain it in their write-up. It's some sneaky thing that they had to do to make this work the way they wanted. It's not described in the data sheets any way I could see, but I checked the circuit board and this is correct. Anyway, so it's dividing the input signal by 10. So we're taking 40 megahertz up to 512 megahertz and knocking it down to 4 megahertz to 51.2 megahertz by function of this chip. Once again, the output is ECL levels, so we have the same exact circuit here as we did up here to take the ECL levels and convert them to TTL levels. Okay, now we have the multiplexing. This is a single chip multiplexer. It can take, it's a dual multiplexer actually. It can multiplex 4 inputs to an output and another 4 inputs to another output. Both of those multiplexers controlled by a 2-bit binary programming input. Bit 1, bit 2, or bit 0, bit 1. It's these 2 bits. And then they control these. So essentially, if you've got 0 and 0 logic on these, then it's going to let one of these signals go through, and also one of these signals go through. If you have 0, 1, it's going to let the next one go through and the next one go through. 1, 0 will give you the third one, the third input to the outputs, and 1, 1 will give you the fourth input going through the multiplexer. So it's picking one of 4 and doing that twice. They've mapped out what's inside the chip here, but it would be simpler just to say it's a 1 of 4 multiplexer. So basically what we have here is the scaled down 4 megahertz to 51.2 megahertz signal. That's the high frequency input, and it's applied to 2 of the inputs of the upper multiplexer. And then the lower one, which is 50 hertz to 50 megahertz, the lower frequency range is applied to 2 more inputs of the lower multiplexer. And then which of those signals goes through depends on what the range switch and the time-based switch are set to. So obviously if you're setting 50 megahertz, you want the 50 megahertz signal to go through the multiplexer. If you've got it set to 512, you want the output of this guy to go through the multiplexer. And that's essentially what it's doing. It's also looking at the time base, but it isn't really changing anything. It's still using the same inputs. It has to. It's sort of peculiar that they chose to put the time base into that and then not really do anything with it. Why are there 2 gangs on these switches? Time base and frequency. Well, the outputs of the 2 front ends are not switched by the switches directly. They're switched by the upper stage of the multiplexer, and the multiplexer is programmed by one of the gangs on this switch and one of the gangs on this switch. Essentially, the center pin's pulled to logic high. The center pin here is pulled to logic high through resistors. In one position, it's pulled low to ground, giving you a logic 0. If the switch is in the other position, or here, then the resistor pulls it up to logic high. So that accounts for one gang here and one gang here, but the other gangs on the 2 switches do something else. On the range switch, this is actually a power switch, because you don't want to have both of these 2 front-end circuits running at the same time. So when the switch is in the 50 megahertz range, only this circuit up here gets power, the 5 volt power that is, and only when the switch is in the 512 megahertz position does the lower front-end amplifier circuit get 5 volt power. Going back to the output of the multiplexer, we've already established in something else I said that the single chip frequency counter IC can only handle a 10 megahertz input maximum. I think I said that. But we're already talking up here about a signal that's 50 hertz to 50 megahertz, 5 times bigger than the chip can handle. And the other one is already scaled down by its or divide by 10 to a 4 megahertz to 51.2 megahertz signal. Also too big. The high end is always around 50 megahertz. So what do we get? When we come out of this multiplexer, we have another divide by 10 IC. It's not the same IC as this one. This one is an ECL chip because of the frequencies it's operating at. And this is just a good old, I think it's a TTL chip. And it's set up, it's actually a divide by 2 and a divide by 5 circuit in one package, and the output of one of them is fed back to the input of the other one. So you get either a 5 followed by a 2 or a 2 followed by a 5. I don't know which offhand. And in order to get a properly shaped waveform, it has to pay attention to two different outputs within the various outputs. There's actually flip-flops in here, and to get a nice clean waveform that's approximately a 50% duty cycle, they have to actually OR these two outputs together. Well, they didn't want to put an extra IC in here just to get an OR, so they just did a diode OR. Two diodes and a resistor to ground forms, well, also with pull-up resistors here. So these two resistors, these two diodes, and this resistor form a OR gate. And so what you end up coming out of here is now a 400 kilohertz to 5.12 megahertz signal if you're on the high frequency range, or a 5 hertz to 5 megahertz signal if you're on the low frequency range, well within the capabilities of the frequency counter IC. Okay, so we've got this nifty intersil single chip frequency counter. Let's take a look at it. It has its own clock and an internal clock generator circuit, and it has a pretty classic crystal oscillator with a couple of capacitors here. One of them is a trimmer for fine adjustment, and the other one is just a loading or biasing, depending how you look at it, resistor across the crystal. But basically it's giving it a 10 megahertz internal clock to do its magic. This version of the chip only has a single digital input. It's called input A. There is no input B. It's called A because some other versions of this chip have two inputs, input A and input B, and they're just keeping the terminology the same. Almost all the other pins are there to drive the LEDs. So it's really designed for an 8-digit display, but because its maximum frequency range is 10 megahertz, if it had an 8th digit, all that left digit would be doing is displaying a 1. It doesn't even need to be a full display. Since they've already limited the input to something that's no more than 5 at its most significant digit, you don't need to have that extra LED display here just to display a 1 that's never going to get used. The biggest thing it's going to display is a 5, and that will be in this position. So they economized a little bit by limiting the frequencies that way. Again, this IC directly drives the LEDs without need for any current limiting resistors. There are 1, 2, 3, 4, 5, 6, 7, and 8 unused digit outputs, and these are common cathode LED displays, so these are the cathode drivers, and 7 out of the 8 are used, and even though the lines go all over the place, they're just connected to the common cathodes of these LED displays, just like you would in any other LED display multiplexing scheme. And then these 1, 2, 3, 4, 5, 6, 7, 8 outputs here, that's 7 segments plus the decimal point, are also brought out in a multiplexing scheme, and they don't show it connected here, but you just have to know that segments A, B, C, D, E, and F are connected across all of these in the matrix. Now they're showing the decimal point wire going to only the 3 displays that actually need to have decimal points. It will always be one of those 3, depending again on the range you've selected and which time base is selected. That will affect which decimal point needs to be on. So the chip's really doing everything at this point. All you need to do is give it that input signal, and it takes care of the rest and displays everything. But you do have to tell it the range. It needs to know what range it's looking at, and that's not referring to the range of the overall frequency counter unit. It's referring to the time base, even though it's called the range here. So the other gang of the time base switch is wired back to the range input. And then you have to tell it where you want the decimal points to be. And normally all you would do is connect one of the digit outputs for the common cathodes and tie those, pick one of them. In other words, whichever digit you want to have a decimal point on. And remember, this chip is controlling the decimal points in a multiplexing scheme, so they're not just always on. They're turned on with that respective digit and then turned off the rest of the time. So the way they've got it set up is you pick whichever digit you want to have a decimal point on and connect its digit output through a switch or through some logic and back to the external decimal point input. And from that it knows when it gets to turning on that particular digit, it feeds back into the external decimal point input. That tells the internal logic to turn on the decimal point output in the matrix scan, and hence you get the correct decimal point on. But it's not quite that simple, because this chip does not know what range you're in. It doesn't know the range, and it doesn't know the time base. Well, it does know the time base actually, but it doesn't know the range. So it's ignorant of whether it's trying to display one or the other. And so that brings me to part 2 of the trickiness of this intersil IC. So again, to conserve pins on the IC, probably no other reason. I already described how it uses the digit outputs as inputs to additional logic, which then get fed back into an input to tell the chip to do additional things. Already discussed the external decimal point input and how that worked. Now the range input has to work the same way, but in this case it's not tied to a particular digit like the decimal points are. And so what they do is the digit 3 output and the digit 2 output are wired over from where they come out of the chip to one side or the other of this gang of the switch. And then the common is brought back to the range input, in other words, the time base input. So by tying either the digit 2 control line or the digit 3 control line from the IC back to its range input, the chip now knows which time base you want it to run in. It actually can run in 4 different time bases. I think it's 0.01 seconds, 0.1 second, 1 second, or 10 seconds. Because the switch here is limited to just 0.1 second or 1 second, we're only using 2 of the possibilities. But in theory we could put in a bigger switch here and connect the range input to 2 additional digit outputs and tell it to operate with even additional time bases. It's certainly capable of doing so. So I already described how normally the decimal point would be controlled if you didn't have any external logic. But again, that simple method I described is just the basic version, and it is not aware of what you're doing out here with the ranges and the time bases, at least not in every way that it needs to be. So what they've done here is they have taken the digit 4 output, the digit 5 output, and the digit 6 output, all coming from here, and connected them through these Darlington transistors, which are just there to boost and isolate the signal. And then those 3 signals are fed back into the second half of the multiplexer, which are under control of the same 2 inputs from the 2 switches. So now depending on which range and which time base you're in, there's 4 possible binary choices there, and this logic will therefore pick. It'll actually use digit 4 twice in 2 different situations, or it'll use digit 5, or it'll use digit 6, and then connect those through, and it comes back out and goes down, and it goes into the external decimal point input. So that is how we tell the chip where we want it to put the decimal point, depending on the positions of those 2 switches. And all this logic is necessary because of the complex way that this IC interfaces all of its control and input, or control and programming inputs, in reference to the matrix scan of the LEDs. So, did I leave anything out? I think I already touched on the fact that normally in a matrix scan LED you'd need to have at least resistors on all these segment outputs. Sometimes you'd also put them on the common cathode lines as well. But this chip, in addition to all the other things it's doing, has current regulators built in, so it's always controlling for optimal current in the various segments, whichever ones are turned on, and it's making some internal adjustment to get the current just where it should be. No resistors required outside the IC. So I think that's the whole thing. I hope you found this to be interesting.